plane in a different manner than when we're trying to understand stability and control. We will try to understand an airplane, same airplane, in a different manner. For example, when I'm talking about performance, even if there is an airplane, our approach in understanding it was through point mass model. That is, we assume that all the masses are concentrated at the center of mass. Why? Because this was okay for us, because we wanted to know the response of this airplane in a rectilinear motion, a response of this airplane for the given external forces. Right? No angular rotations were considered. Since no angular rotation was considered, so we are happy with a point mass perception. And in that, the moment I talk about performance, this diagram was good enough.
Dude, I hate that. Ugh. I hate that chalk. I hate that. It's like cringe. But yeah, I have to finish 1.1 today itself because I have to finish 1.1. This is until 2:37. So this is chapter 1, aircraft stability, aircraft stability, lecture 1.1.1. Use use this abstract as an example to explain what is going on.
thrust equal to drag, lift equal to weight. That was good enough, and we took each. What is the
So, in studying performance, we treat the aircraft like a particle. So, meaning we care about the speed, we care about the altitude, we care about the climb, we care about the range, we care about the fuel, we care about the trajectory. Come for more.
And this dive.
Your stammer.
Wait, wait.
You're the biggest pedophile protector in history. And God is watching, and you will pay for what you've done to England. And we need a new prime minister that has guts and that's gonna stand up for the British and send all of these rapist Muslims and dirty rugs back to their Sharia nations. Yeah! God bless England. God bless the United States of America. And Christ is King.
And you'll see it again on Saturday at a march designed to confront and intimidate this diversity and this diverse country. That is why this Labour government will block far-right agitators from travelling to Britain for that event. Because we will not allow people to come to the UK to threaten our communities and spread hate on our streets.
significance of having CL by CD maximum.
This is lecture 1.1.2. Am I right? Yeah. Lecture 1.1.2. So there's a performance analysis. So what we have is, so we treat a, what in the world are those? Holy shit. So while studying about performance, so when studying about performance, you treat the aircraft like a particle. So you treat aircraft like a particle, which means you care about the speed, which means you care about the speed, you care about the altitude, you care about the climb, range, fuel, trajectory. So you care about speed, you care about altitude, climb, range, fuel, trajectory. Range, fuel, trajectory. So everything in between. Now, obviously, you don't care about rotation because airplane, airplane having a rotation. Come on. I mean, yeah, airplane does have rotation, but you don't really care about rotation, right? Like, who cares about rotation? Because you're not even going to focus much on rotation, right? Because rotation is something that you're not going to focus on. You're going to focus on speed, altitude, climb, range, fuel, and trajectory. It's not going to rotate like a jet does. Jet, I mean, even a jet, you're not going to focus much on rotation. Who cares about rotation? Because rotation is not affecting what's going to happen to the plane or whatever, unless something bad happens, right? So a plane's a plane is simplified into F is equal to ma. This is the entire thing. The entirety of what an airplane is simplified to. The entirety of what an airplane is simplified into. So you have F is equal to ma. So you have the main force, you have the thrust, the drag, the lift, the weight. The main forces, the key forces. So key forces are thrust, drag, lift, and weight. You're gonna have C of T, C of D, C of L, C of W. In a steady flight, the thrust is equivalent to the drag force and the lift force is equivalent to the weight force. Thrust and drag, because if you look at a rocket here, they have a thrust. If let's say for an airplane, for example, thrust, drag, so meaning is going forward, and then drag, and then lift, and then the weight, right? So what happens in a steady flight? So steady flight, you're gonna have a thrust. So going forward, have these are the thrust force. This is the drag force. That's the lift force. And that's the weight force. So typically the airplane is literally a moving particle, right? So this entire airplane is literally a moving particle. But that's for an airplane. That's not for a rocket, though. Now, a rocket. What happens in a rocket? So your rocket abstract starts beyond this level. So your abstract is not just performance, it's stability plus guidance plus control. Because now the vehicle rotates, deviates, oscillates, becomes unstable, and no angular rotations are considered. That's the key. For rockets and missiles, small disturbance will be very, very dangerous. So if there's a wind gust or a thrust asymmetry, then a little change, little change, poof. So let's say, for example, if there's a wind. So let's say you want to launch a rocket, right? And if there's wind, they're literally going to stop the rocket launch. They're literally going to stop a rocket launch. Why? A little wind, a little wind. Let's say it's going up, 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 right? And if there's a little wind, it can tilt. And when it tilts, it'll change the direction of where it is supposed to go to a different place. And if the wind is higher and higher, it's going to keep blowing to a point where the rocket will be like falling down and right. So even if there's a little, like, it must be like the wind can be there. I'm not saying wind will not be there. Wind can be there, but there's also a limit as to how much wind should exist, because if you have too much, then pretty much you're done, right? So why point mass fails in rocket? Why point mass fails in rockets and missiles? So for rockets and missiles, small disturbances become dangerous. For small rockets and missiles, small disturbances will be dangerous. If there's like wind gust or thrust asymmetry or anything that will hamper the launch of a rocket or a missile, it's going to be bad. So, for example, if you have the wind gust or thrust asymmetry, or you have the change in fuel mass, the change in fuel mass, whatever, any uncertainty. So we'll just say any existing uncertainty. So any existing uncertainty is going to create a pitch rotation, roll rotation, yaw rotation. So it's literally a rigid body now, right? So many dangerous rotations will occur. So many dangerous rotations will occur. So initially in the performance model, the older part, like the general part, so MA will be T minus D minus mg. So there is no rotation included. In a stability model, you're going to have rotation included. So we're going to include the rotation dynamics. So for example, for a pitch motion, you're going to have the moment of inertia multiplied by the pitch rate. The differentiation for a pitch rate is the pitching moment. Now the rocket can rotate, which changes everything. Older models, so case one, older models just hoping if she's okay. I hate how I just hate how she gets this much hate. Like, come on. Yeah, it's not right. I think that yeah, it's not nice. It's not nice. It's not nice. They don't understand like what she went through to even she's literally risking herself for you know people don't understand it. People will never understand it. Only thrust, drag force, and weight force included. Now here on the newer models, so we include the rotation dynamics. So you have the inertial model q dot is equal to m. So so I of yy is the moment of inertia. Q dot is the pitch rate, and m is the pitching moment. So the small errors can create rotational destability because this time, as the moment appears, the rocket will pitch, the angle will change, aerodynamics will change, everything changes. So when those small mismatch are created, so when those small mismatch is created, everything changes. Those long story short, drag, aerodynamic force, angle, rocket trajectory, everything changes. So error, rocket trajectory, angle, aerodynamic, everything changes. Everything changes. Yeah, let's not go too far. Let's not go too far. Aerodynamic center. We are in actually wait, what 3 2 so uh 7, almost 7. So again, they're going to use airplane examples, but let's not use airplane example. Let's use the rocket and missile as example because the professor will focus on airplane. Let's not explain. Let's not understand airplane. Let's understand rocket. Let's understand the rocket and missile example. Use my abstract and explain that thoroughly. So earlier the rocket was treated simply like ma is equal to summation of f. So we only care about the thrust, the drag, the velocity, the altitude, and the range. Just like airplane performance, we ignore the rotation. So if the rocket generated enough force, the thrust will be greater than the drag force plus the weight force. So it will climb. Simple. Now the stability changes everything. We ask, what if the aerodynamic force does not act perfectly through the center of mass? This is where the rotation will begin. This is where the moments will appear. This is where the stability matters. For airplanes, the aerodynamic center is usually near the C1 by 4, the quarter chords, because the aerodynamic force acting away from the center creates rotation. Acting away from the center of rotation, so like if this is an airplane, so like somewhere here, that'll create a rotation. So for rockets and missiles, we usually discuss center of mass and center of pressure. Center of mass is where the total mass acts like fuel mass, body mass, payload mass combined into one effective point. The center of pressure is where the aerodynamic forces are effectively act, meaning the wind hitting the rocket can produce a pressure, can produce a lift-like forces, and can produce side forces. So it can create more pressure. So as it goes up, like if it reaches space, then obviously the pressure will increase, right? Or let's say if the wind is gusting and if the rocket is going up, then it can blow out. Or if there's like more wind at the top, like from bottom, if there's more wind, they can be, so it's going to create more push, right? So there are uncertainties everywhere. Now the entire stability problem becomes, where is CP, the center of pressure, relative to center of mass? So this determines whether the rocket is stable or unstable. And so suppose wind hits the rocket sideways slightly, so the aerodynamic force will be F of A. But if this force acts away from the center of mass, then M is equal to R times F. A rotational moment appears. Now the rocket pitches or yaws. Okay. If the center of pressure is less than center of mass, then the aerodynamic force creates the pressure center behind mass center. Can you show a picture? Can you show a diagram or a picture of where CP and CM exist? Because you have too many words, but no diagram to show. Okay, center of mass is there, center of pressure is here. So this is the entire rocket. The moment rotates, because CP is behind CM, the moment rotates the rocket back to, what does that even mean? Like, you don't make sense, but I'm really trying. I am really trying to understand. So that's a stable rocket, all right. And unstable. So let's say, why is it unstable? Because now the aerodynamic force, the pressure is at the top, the mass is at the bottom. Now explain the entire thing using diagrams. Now explain all those. Now explain, use my example, use my abstract, and explain using diagrams. Because you have too many words. Like, too many unnecessary words which actually overlooks the core key concept, and I had to understand without a diagram. Oh yeah, man. She knows that. Okay, thank God. She's not going to read this. She's tired of it. All right. So the performance model, the rocket performance model. Rocket performance model. So obviously, in performance, you're only going to care about the thrust, drag, velocity, trajectory. So in a performance model, in a so if actually we explain that, if I had to draw this, let's say this is our rocket, and CM will be like somewhere here. So that is CM, which we will call center of mass. And the performance will only ask for thrust, drag force, weight force. So this is performance model. However, there is no rotation. However, no rotation exists. So, however, no rotation exists. All right. Just go up, 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 up. Oh shit. Okay. So that's at the C by 4. So this is at C by 4, quarter of coefficient. Now your abstract begins here. So now disturbance matters. So example, you have wind gust, you have the thrust misalignment, you have the aerodynamic uncertainty. Now the rocket will rotate. So now you have this will be 2 stability view. So now you have the disturbance. Now you have like the wind gust or thrust misalignment. So you have wind gust, thrust misalignment, thrust misalignment. Got the aerodynamic uncertainty, aerodynamic uncertainty. So obviously now the rocket will rotate, right? So now rocket rotates. Now rocket rotates. So the aerodynamic force will create the moment. Now if I were to draw the rocket again, we're going to have Cm like somewhere here. So that'll be Cm, Cm being the center of mass, and Cp being the center of pressure. And R is the distance from Cp to Cm. And the aerodynamic force is F of A, which creates the moment. So aerodynamic force is what? Our aerodynamic force F of A. So we have M is equal to R times F of A. So that's the pitch moment. The uh, pitch moment is equal to the distance from Cp to Ca multiplied by the aerodynamic force. So pitch rotation moment is equal to a distance from Cp to Ca multiplied by aerodynamic force. And a stable configuration. So if the wind pushes the rocket, moment will restore the rocket stable. If the wind pushes the rocket, if Cp is behind Cm and the wind pushes the rocket, the moment will restore the rocket. Okay, makes sense. If the wind pushes the rocket, there's a pressure here. Oh, it makes sense. Because there's pressure on the rocket, it's gonna stop so that it does not rotate. Ah, now it makes sense. Now it makes sense. But if the CP was at the top, and because there's pressure, right? So it's the wind adding in the pressure. It's like you're hungry and you want to eat more. So it's like it's gonna add more, more, more. So it's gonna go all the way down. Makes sense. Makes sense. So stable configuration where if let's say this is my rocket, this is a stable rocket, and let's say the flight is going upward, so it's going upward thrust. This is our center pressure. This is our center mass. Now, if the wind is blowing this way, this Cp will prevent the rocket from toppling over. Rocket from toppling over, which can, because more pressure is added to prevent that toppling. Because Cp rejects equal amount of wind force, the equal amount of force that the wind is applying on Cm. Because Cp rejects equal amount of force. Cp rejects equal amount of force. So Cp rejects equal amount of force which the wind appends towards the Cm, which the wind appends towards the Cm. And if the wind pushes the rocket, the moment will restore the rocket. So stable. So this is stable. Unstable. This is unstable. Cp, Cm, and the wind is blowing. This is unstable because now not only the wind will push, but the pressure will actually engulf that wind force and it'll easily topple over. Here, the wind is blowing towards Cp, which will, and because Cm cannot reject the equal amount of force, like CM cannot give away equal amount of force like CP can, it'll topple over. Cannot give away equal amount of force CP can, it will topple over.